well, let's learn about static friction. Now, first of all, keep in mind that static means that something's stationary, while the word kinetic means that it's in motion. Static friction is a little bit trickier to understand than kinetic friction is, which might be surprising because it seems like if things are moving, that's more complicated. But it turns out with friction, static friction is a little more subtle than kinetic friction is. And this is why. Imagine that you have to move some furniture. Maybe you have to push a couch or a refrigerator across the floor. You've probably noticed that when you do this, you will start pushing and the furniture doesn't move. So you push a little bit harder. It still doesn't move. And then you're like, all right, I'm gonna push really hard, and finally it does move. So what was happening there is that static friction was adjusting with your push. When you first pushed just a little bit, static friction applied exactly the right amount of force opposite to your push to keep the couch or the fridge from moving. Then you pushed a little harder, and static friction pushed a little bit harder the other way. And at some point you pushed so hard that you exceeded the limit that static friction could push back with. And then the object started to move, at which point kinetic friction took over. So we can sum up that behavior in a graph. On the horizontal axis is the force that you're pushing with. So your push gets stronger and stronger as this goes to the right. On the vertical axis is the magnitude of the static friction force. And again, just think of a couch that's kind of stuck to the floor. You start pushing, it doesn't go anywhere. So as your push increases, the static friction force increases with that push. It's the same value as your push. So these two forces, the static friction force and your push force, I know we're using the letter F twice here, but lowercase f is traditionally used for friction, and uppercase F is traditionally used for an applied force, like you pushing on something. So these two forces are equal to one another. That's why this is a straight line at 45 degrees. And then finally, at some point, the floor is only so sticky, the floor can only apply so much friction, and now the couch starts to move. And you see that this friction force suddenly drops down, and now you're in the kinetic zone where the object's moving. And it's generally true that kinetic friction is less than the maximum amount of static friction. And kinetic friction is just a constant value for the most part, whereas static friction varies with the amount of applied force that you provide up to some maximum value. So that's kind of complicated behavior, but keep in mind that when a textbook gives you a coefficient of static friction, that coefficient is really referring to the maximum value that the friction can have. Keeping in mind that any value less than that maximum is also possible. So we say that the force of static friction varies between 0 and some maximum value, where that maximum value equals this coefficient of static friction times the normal force. So if you look up coefficient of static friction, it'll give you this number, but keep in mind that that's really a maximum. It's possible to have static friction that's less than that. fact, it's not just possible, that's what happens as long as your push is less than the maximum static friction force. All right, so let's do an example problem. Example 4.6 from your text. And this involves a block on a slope with friction. All right, we've got a block of mass 4 kilograms with a slope of angle 30 degrees, and there's a coefficient of static friction equal to 0.65. Coefficients of static friction or of kinetic friction don't have any units. And you can see that in this equation. There's a force, and for normal force is also a force. So F and N have the same units, which means that mu can't have any units. It's just a number. That's why it's called a coefficient. And we want to answer several questions about the situation. First of all, what's the normal force? What's the maximum static friction force? What's the actual static friction force? D. And finally, will this block move? All right, there are questions. Now we can analyze the situation with a Newton's second law approach. So I'm going to go draw a free body diagram over here because I have space on the board. Now this is one of those weird situations where we need to use a tilted coordinate system. I make sure that the x-axis goes along the slope because that's the direction of motion or potential motion, and the y-axis goes normal or perpendicular to the slope. And there's my object of interest, the block. I get several forces. There's gravity that points straight down. There's our angle. We've got the normal force of the ground on the block. And the friction force opposes the direction of motion or of the intended motion, and that is the friction force of the ground on the block. And we should resolve this gravity force into x and y components. There's x, there's y, and if you look at that right triangle, the x component will get sine, and the y component gets cosine. Okay, so let's let's write down Newton's second law for the y direction. Newton's second law in y. Okay, the sum of the forces in the y direction equals MAY, but that y acceleration is 0 because that block is not moving. It's supposed to be a 0. That block is not moving perpendicular to the slope. So we've got n minus wy, which was w cosine theta equals 0. So that means that n, I'm going to drop the subscripts, equals w cos theta, and w, the gravity or weight, is mg. Oh, so we've answered part A. What is n? And if you plug in these values, it gives you 33.9 newtons. Right, 33. And I've said this before, but it's worth mentioning again. We've only got so many letters in the alphabet. The n over here means normal force, the n on the right means newtons. That's some horrible notation, but we're kind of stuck with it. Sorry. I think the textbook might use a lowercase n, but it's also common to use uppercase n for normal force. All right, well, we found the normal force, which is great because now we can find, so that was the answer to part A. So now we can find the maximum static friction force. Right, that equals mu times n. And so with the values that they gave us, this is 22.1 newtons. All right, part C. What's the actual static friction force? So we'll just kind of assume. Let me step back here because questions C and D are a little bit subtle. We're trying to figure out if this block is going to move. Is this static friction actually enough to hold the block in place against the force of gravity? So what we'll do in part C is we'll assume that it doesn't move, see what value the friction force has to be to hold it in place, and then in part D we'll compare the force we get to the maximum force that static friction could have, and if this is less than part B, then static friction is capable of holding it in place. If our answer to part C is greater than our answer to part B, it means that the static friction force actually isn't strong enough, and our assumption that it was stationary is wrong, and the block would move. Okay, so let's assume that it's not moving, do the analysis, and see what we get. All right, so here's where we make this assumption. assume that that's 0. Assume the block is not sliding down the slope. So if that's true, that means the x component of gravity minus the friction force equals 0, which would mean that the friction force equals W sine theta, or mg sine theta. Putting in the numbers, that gives 19.6 newtons. So what this means is we need 19.6 newtons of force to hold that block in place against gravity. Fortunately, this static friction is more than capable, because this can provide up to 22.1 newtons of force if needed. It's not needed, so this actual static friction force is this value. Because remember, static friction takes whatever value is needed to hold an object stationary up to some maximum point. Since we didn't exceed the maximum, then static friction is this value. So there's our answer to part C. And that means that our answer to part D is no, the block does not move. It's stationary. All right, I want to do one more example in this video. So I'm going to erase this stuff. So I'm going to use, this is no longer example 4.6, this is just an example that I made up, my example. So same situation, I'm not using any particular values this time, just keeping these as variables. And the question I want to ask is, what is the maximum angle that we could have before the block starts to slide? So you can imagine starting at a small angle, and static friction is more than capable of holding the block in place. But as you tilt to greater and greater angles, the x component of the gravity force gets bigger and bigger. And at some point, the static friction force is not going to be able to hold the block on the slope, and it will start sliding. So let's see where that occurs. That would occur when the static friction force, which is trying to balance out this gravity force, equals that maximum value. So our analysis can start in this x direction. And we're assuming, again, that this block is stationary. So we've got the friction force friction force is negative. Gravity's positive. Wx minus friction force equals 0. And we got to think about what's going on here. When you reach that maximum possible angle, this is still 0. And once you slightly exceed that maximum possible angle, then the thing starts to accelerate and the right-hand side becomes non-zero. So what we're going to do is assume that the friction force gets replaced by this maximum value, and the right-hand side is still 0, but this situation is when the block just begins to slide. So that's saying the max static friction force equals mg sine theta, and this was mu s times n. If you recall from the example we just did, that n is mg cos theta. These mg's cancel out. You can divide both sides by cosine, and you get this relationship, mu s equals sine over cosine, which is tangent. And I should say this is the maximum angle now. And so we can solve for that maximum angle. Inverse tangent of the coefficient of static friction. So this is kind of interesting. The maximum angle doesn't depend on the mass at all. It only depends on the coefficient of static friction. All right, that's the end of this video. See you in the next one.